All right, guys. So next tutorial is going to be over the form I just handed out: percent composition, empirical, and molecular formulas. There's kind of a lot going on with this piece, and it's just going to take some practice. I know this assignment's a bit of a bear. I'm going to give you a couple days to get it done, but I'm going to go over 4 of the problems with you. So we'll go over page 1, number 3, page 3, number 5, and then I'll slide the board over. We'll do page 3, number 9, and then page 4, number 12. All right, so things to have in front of you, of course, would be this paper, which is stapled, hole punched for you. And then, like always, calculator, periodic table. Now, again, I know I say this often, but while we're working through the questions, pause and try to work them out yourself. You know, you guys don't want to get too good at watching me do chemistry. All right, I'm here to support you, but you got to be able to do it by yourself. So pause. Try to work the solution out by yourself, see how it goes, and then if you're confused or stuck, you just want some help, hit play and see how I go through it. Obnoxious bells. Okay? So we will go ahead and begin with page 1, number 3. So that's this guy highlighted right there. Okay? So I kind of truncated the wording here. It says 1.2 moles of carbon and 3.2 moles of hydrogen. What is the percent composition by mass? All right. So again, I kind of just put the important bits of what it says. It doesn't say exactly that on the paper, but we want to know the percent composition, right? So percent composition by mass. That means we need to get our numbers in terms of mass first, right? And so the 1.2 and the 3.2 are in terms of moles, right? But lucky for us, we've already learned how to convert moles into grams, right? We multiply by the molar mass, so pretty simple, all right? So here we're going to turn our carbon, 1.2 moles of carbon into grams, all right? And then we're going to turn 3.2 moles of hydrogen into grams, right? Then once our comparative numbers are in mass, we can then go ahead and identify that percent composition by mass the way you've been taught. All right, so I have 1.2 moles of carbon. This is number 3 from page 1. Carbon, right? Now I want to convert that into grams. So I'm going to go moles bottom, grams top, right? Over 1. Now, of course, I go to my periodic table and I find that my molar mass of carbon is 12.01 grams, right? And again, I know to multiply there because I'm going out of moles. I'm in moles, going out. That means we multiply, so my mass goes on top. And what that'll give me in this case is 14.4 grams of carbon, right? Now I'm going to follow that up with a quick calculation for hydrogen. I have 3.2 moles of hydrogen. Over 1 moles to grams. 1.01 grams per mole. Again, that's the number I get from my periodic table. I go ahead and I run that calculation out, and I should get 3.23 grams of hydrogen. All right. So now my mass, my amounts are in grams, so that I can do a comparative percentage by mass, percent composition by mass. Right. So in grams, go ahead and underline my units there. Cross cancel my moles, because I like doing that. All right, so I'm in grams. Now I can do my percent composition. Remember, percent composition is just a part divided by a whole. All right, so I want to know what percent carbon I have and what percent hydrogen I have. So I'm going to set it up just like this. I'm going to leave those numbers up there for reference. I'm going to erase my work here. Right, so I have those amounts in grams. So if I want to know my percent carbon, I'm going to take my part that is carbon over or divided by the whole, which would be 14.4 plus 3.23, right? And take that number times 100, right? And when I do that, I should get 81.7% carbon, right? So again, what did I do? I took my part that was carbon in grams, which I had calculated just a minute ago, and divided it by the entire mass, which is the 2 together, right? So likewise for hydrogen, if I want to know what percent hydrogen I have, I could do this one of two ways, right? I can plug it back into an equation, or since there's just two elements, the easy thing to do is just to go 100% minus 81.7%, right, equals 18.3% hydrogen. There's my answer, right? Now, if you have more than two elements in a formula, so you got more than 2% or two masses to deal with, of course we can't just subtract from 100 for that second one, right? We have to plug it back into the equation. So I could have just taken my amount of hydrogen, 3.23, and put it on top and then divided by the total, and then times 100, I would have got the same answer in this case, okay? But subtracting from 100% only works when you add just two elements. Otherwise, you got to find the other 2 or 3 before you can subtract that last one, okay? So, what do we have to do for this one? This says we're in moles to start, so I had it, and I want to know the percent by mass. So I converted the moles into grams first, so I'm in mass. And then you take the part of divided by the entirety. So we have a certain, so 14.4 grams of carbon, 3.23 grams of hydrogen, right? That's our entire. So the part that was carbon, which would be 14.4 divided by the total times 100%. Then we can subtract that from 100 to get hydrogen. Okay? So that is how we can do percent composition if we're starting in moles. Gotta get into grams first. All right. So we're going to move on to page 3, number 5. All right. So page 3, that's the one at the very top of that page, right? And it reads, a compound with an empirical formula of C2OH4 and a molar mass of 88 grams per mole, right? What is the molecular formula of this compound? So in this case, I'm already given the molecular formula, or the empirical formula. So if you remember, empirical formula is the same ratio of elements as the molecular formula. It's just been reduced to that to the lowest whole number ratio, right? And so often, not always, often the actual molecular formula, we're going to have to increase our subscripts by the same factor to actually get the molecular formula, okay? And the way we can figure out our molecular formula from our empirical formula is if we know the molar mass or molecular mass of the molecule, okay? So I know that this is my empirical formula, which may or may not be the same as my molecular formula, all right? There's one way to find out. So what we do is, this is our formula. So if we already know our empirical formula, this is basically a two-step thing. It's simple, right? It's molecular mass over empirical mass, okay? Or we could do molar mass over empirical mass. Either way, it's either AMUs or grams. Our number comes out the same, okay? So what we want to know is the molecular mass, which is given to you in this equation. So I'm going to say equals 88 grams per mole divided by my empirical mass. So if my empirical mass comes out to the same number, I know that this would be 1, and therefore the empirical formula would be the same as the molecular formula. But this, when I divide, should come out to close to a whole number, whether it's 1, 2, 3, or 4. Okay? So I'm going to take 2 carbons plus 1 oxygen plus 4 hydrogen. I'll punch that in my calculator. I'm not going to show you guys how to do it because you should know that by now. All right? And when I do that, I should get 44 grams per mole, or really close to it. Right? I'm kind of rounding things to make this easy. Right? When I divide, I get 2. Right? Now, that 2 tells me what number to multiply the subscripts in the empirical formula by. Right? So my empirical formula is C2OH4, right? So there's my empirical formula, C2OH4. Now, my molecular mass is actually double that. So that tells me that I need to double the quantities in this empirical formula. I'll have the same ratio. It's just going to give me a better picture of what that molecule actually is. So I'm going to take 2 times 2, which is be C4. 2 times 1, O2, 2 times 4, H8. And that is my molecular formula right? So again, if you already know your empirical formula, you also have to know the molar mass or molecular mass. If you know those two things, right, we can go ahead and figure out our empirical formula real quick. All right. Now, sometimes we don't know the empirical formula. We maybe only know a percent composition. Okay, that adds a few steps to what we got to do. Makes it a little more complicated. Not hard, just more steps. Okay. So, and that takes us, by the way, to number 9 from page 3. So I'm going to go ahead and change boards here real fast, like I said I was going to. Bam, ready to go. See how prepared I am? I already have that written up there for us. All right. So number 9 from page 3. Right. So this one, you can see already there's a little bit more work involved with this one. It says nitrogen and oxygen form an extensive series of oxides with the general formula NXOY. So we're going to have to figure out what these numbers for nitrogen and oxygen are empirically. So that means within their ratio for this question, right? So we want to know what the empirical formula is if in a particular compound we're looking at, we have 36.84% nitrogen. All right? So again, we could have different nitrogen oxides with different percent compositions. In this case, this particular nitrogen oxide is 36.84% nitrogen. All right? So first of all, we're only given one percentage here, right? Out of the two, but how hard is it to find that other one? It's not. We just subtract it from 100. So first thing I'm going to do, right? So I know I have 36.84% nitrogen, right? So my percent oxygen, then it stands to reason would be 100% minus 36.84%. And when I do that, I should get 63.16% oxygen. All right? So now that I know my percent for each one, right? I know which percent oxygen I have, and I know my percent nitrogen, right? I have enough information now to go ahead and figure out my empirical formula. All right, so it's 3 steps. The first step is going to be dividing the percent composition by their atomic mass, okay, which we get from the periodic table. All right, so for nitrogen, okay, I'm going to take 36.84%. I'm going to divide that by 14.01. Now 14.01 again is that number I get from my periodic table just by looking at the atomic mass of nitrogen. And when I do that, I'm going to get 2.63. Okay? Now I'm going to do the same thing for oxygen now. All right? I already have my percent, so I'm just going to leave that over there as a reference. So for oxygen, I have 63.16% over the atomic mass of oxygen, which is 16.00. And when I do that, I should get 3.95. All right, so what I've done in that step, and that's our step 1 that I showed you guys in class from that last PowerPoint show, all right? What I've done is because oxygen and nitrogen have different masses, and we have that percent by mass, I've kind of gotten the mass part out of the equation. I want to know really my ratio of oxygen atoms to nitrogen atoms in that formula. So by dividing by the atomic mass, I kind of take the mass out of the picture. Okay? Now I actually have a ratio, but I want to turn this into whole numbers, right? This is kind of hard to spot. Some of you can build math and people can maybe pick it out real fast. But the way to turn this ratio that's already there into a whole number ratio is simpler. Is you take the smaller of the two, right? And you guys should be able to do that. That's this small number right here. We're going to divide both quantities by the smaller of the two. So of course the number divided by itself gives me 1. If I go 3.95 divided by 2.63, I actually get 1.5. All right? Now, what did I tell you if a number comes out to 1.5? Do you remember that? Okay, so typically, remember, we're rounding these to the nearest whole number. When it comes out kind of spot in the middle like that, right, we have to assume then that we have to adjust our ratio a little bit. So when it comes out in the middle like this, we're going to multiply both numbers by 2. So my real ratio would actually be 3 to 2. All right. So what that tells me is I have 3 oxygens for every 2 nitrogens, and that is a ratio, right? And that would be my empirical formula. So if I'm going to go NXOY, my empirical formula would be for nitrogen N2, right? And then O is 3. O3. There is my empirical formula. All right? So again, what did I have to do in this question? I start with my percent composition. In this case, I had to first get my percent also for oxygen. That's why I did that little first subtraction problem first. So I knew that I had 63.16% oxygen and 36.84% hydrogen. I wanted to get those out of mass equations, so I divide them both by their mass. And that gave me these two numbers, 3.95 and 2.63, right? When I have those numbers, I actually have a ratio, but it's a little harder to spot in those goofy numbers. So what I do is I take the smaller of the sample and divide it into all of them, and I get a 1 and a 1.5. You have to remember then, if it's a 0.5, right, we have to then double the quantities for both. So that puts this to 3 and this to 2. And there is an empirical formula. Now, 2/3 is a fraction that can't be simplified, right? So that's the way you can always tell, is it an empirical formula or not? Can I reduce my fraction, right? If I put 2/3 into a fraction, can that be reduced? The answer in that case, no, you can't simplify that, okay? So there's my empirical formula. All right, that was number 9. So we're gonna get to the crux, and I know we're getting a little bit long here, such as life. Number 12 on page 4, there's a little bit more going on. So what we just did here, right, is we went from percent composition to empirical formula. Now, if we know empirical formula and we know the molar mass, right, we can then figure out our molecular formula. So if we can go percent composition to empirical formula, boom, that's what we just did. We just need to go that other step, like we just did on the other board, going from empirical formula to molecular formula. All right? So it might be helpful to kind of split that into 2 separate problems altogether. All right? So that's what we're going to do for number 12. So nicotine is 74.1% carbon, 8.6% hydrogen, and 17.3% nitrogen. All right? We're also given the molar mass in this case, which is about 160 grams per mole. So that's enough information right there to figure out a molecular formula. We just got to go through some steps. First step, what's our empirical formula, right? So how do we do that? If you're given percent composition, we want to get them out of mass into a ratio, right? So we're going to divide each of our percent masses by their individual mass. All right, so first step here, I have carbon, hydrogen, oxygen, and nitrogen. So I'm going to find carbon, which would be 74.1 over 12.01, and that gives me 6.17. Next step, hydrogen is 8.6 over 1.01, and that gives me 8.51. And nitrogen, in this case, is 17.3 over 14.01, and that gives me 1.23. All right, so now I have a ratio, but it's in these ugly numbers, and it's hard to actually pick out and reduce those fractions, if you will. So we're going to simplify our ratio. We're going to take the smallest one, which is 1.23, and divide it into all of them. So when we do that, we always get one that comes out to a 1. This one comes out to 6.92, which means we're probably going to have to round that to 7, right? And this, when I do that, comes out really close to 5, so I'll go ahead and round that. All right? So now I can get my empirical formula. It's going to be C5H7O. There's just a 1 oxygen in that form. All right? So, oh my goodness, not O. N. Close one. Nitrogen, not oxygen. All right, so C5H7N is my empirical formula. That means my molecular formula is going to be some ratio that looks like this, but maybe it's double or triple what it actually shows in my empirical formula. But my ratio is going to stay the same. So I found my empirical formula like this. Here's my ratio, 5 carbons to 7 hydrogens to 1 nitrogen. All right? So that's my empirical. I got to go one step farther to get my molecular formula. All right? So how do you find molecular formula from your empirical formula? All right? You take molar mass, right? Over empirical mass. All right, so we're given our molar mass is 160, about 160, right? We're going to divide that then by the mass of this empirical formula, which is 5 carbons plus 7 hydrogens plus 1 nitrogen. So I push that in my calculator, and I get 83.12. Now we can eyeball this and tell it's not going to come out to an exact whole number, but it's going to come out really close or close enough to 2. All right, so again, we're doing lots of rounding up or down to a closest whole number in these situations. We don't round when it comes out to a 0.5, means we double everything, but if it comes out real close to a whole number, we just round to the whole number. So this comes out pretty darn close to 2, all right? So now that tells me that my molecular formula is double my empirical formula, right? So C5H7N is going to become, for carbon, 5 times 2, C10, H14, N2. So that would be my molecular formula for nicotine. All right, that took 22 minutes almost, all right? A quick run back through. We get rid of our percents by dividing by the molar mass or the atomic mass of our individual elements, right? That gives us a ratio. It's an ugly ratio. So we divide by the smallest of those quantities into each of them to get a whole number ratio. That gives us our empirical formula. We divide the mass of our empirical formula into our molecular mass to figure out what we multiply our subscripts by. We go through and multiply that, and we get our molecular formula. All right? That's a lot to be getting on with, but just practice. That's why this sheet's so long. You're going to get lots of practice with this.